Right now, somewhere on this planet, a developing human embryo is quietly building a tail. Not a figure of speech, an actual physical tail with its own small set of vertebrae extending from the base of the spine like something you'd expect to see on a completely different species. And here's the detail that should sit uncomfortably with you. Every human embryo does this. Yours did, mine did. And by the end of this video, you'll know exactly why that tail vanishes before birth, and why the real scientific explanation was only pieced together a few years ago, thanks to a burnt-out graduate student, a shattered glass jar, and one badly timed cut on his finger. Let's start with the part biology class conveniently skips over. Somewhere around week 4 or 5 of human development, embryos grow a structure called a tail bud, a genuine tail complete with somewhere between 10 and 12 tiny vertebrae. For a short stretch of time, human embryos look remarkably similar to the embryos of other tailed creatures, fish, mice, even other primates. Then, over the weeks that follow, that tail gets pulled back into the body. Its cells get repurposed. Its length shrinks, until all that remains is a small fused cluster of bone at the base of your spine. You already know it. It's called the coccyx. Or, if you've ever slipped and landed hard on a hard floor, you know it as the bone that ruins your entire week. Every single human being alive right now is carrying around the unfinished blueprint of a tail we simply never completed building. Which raises the obvious question, why does that construction project get shut down partway through? And more importantly, why did our ancestors lose the tail in the first place? For a long time, the answers people offered were essentially educated guesses dressed up to sound scientific. Maybe tails became less useful as body size increased. Maybe they were an unnecessary energy cost. These theories weren't crazy, but none of them were actually testable, and none of them explained the specific genetic mechanism that caused tail loss to happen in the first place. You can speculate about why evolution might favor something all day long, but without identifying the actual molecular switch responsible, you're telling a story, not proving one. Here's where it helps to zoom out. Nearly every vertebrate on Earth has a tail. Fish have them. Reptiles have them. The overwhelming majority of mammals have them, including most primates. Monkeys swing through forest canopies with long, dramatic tails trailing behind them, sometimes using them almost like an extra limb. New World monkeys in Central and South America push this further, evolving prehensile tails strong enough to grip a branch and hold their entire body weight, essentially turning the tail into a fifth hand. And then you get to the apes: gibbons, orangutans, gorillas, chimpanzees, bonobos, and us. Not one of them has a tail. Somewhere around 25 million years ago, the common ancestor of every ape species lost its tail entirely, and that tailless body plan got passed down to every single descendant that followed. That's a strange thing to happen to an entire branch of the primate family tree. For decades, scientists could see the pattern clearly in the fossil record. They just had no idea what genetic switch caused it. It's worth pausing here because losing a tail wasn't some obviously smart upgrade. Tails are genuinely useful. Old world monkeys rely on their tails constantly for balance, for sprinting along branches, for correcting posture mid-leap, the way a tightrope walker uses a pole. New World monkeys went even further, evolving tails strong enough to hang their entire body weight from a branch, while both hands stay free to eat or groom. In a lot of ways, a tail is remarkably efficient biological engineering, which makes it even stranger that an entire lineage of primates walked away from that advantage completely. That mystery sat mostly unsolved for a surprisingly long time, until an accident in a New York apartment cracked it open. In 2019, a graduate student named Bo Xia was cleaning up his kitchen when he cut his finger on a piece of broken glass. Nothing dramatic, just an annoying trip to the emergency room and a handful of stitches. But sitting in that waiting room, nursing his hand, and presumably bored out of his mind, Xia started thinking about scar tissue, about how differently various animals regenerate damaged body parts, about how some species can regrow entire limbs while humans are stuck forming scars instead. That thought spiraled into a much bigger question about lost body parts in general, and somewhere down that rabbit hole he landed on the tail. It's a genuinely good example of how scientific discovery actually works sometimes. Not through some grand planned proposal, but through a bored, mildly injured person, staring at a waiting room wall, chasing one curious thought to its logical extreme. Xia reportedly went home that same night and started reading everything he could find about tail loss in primates, which is either the most productive reaction to a minor injury in scientific history, or a sign that graduate school does strange things to a person's relationship with free time. Possibly both. Here's the twist that turned an ER visit into a real scientific breakthrough. Xia, working alongside researchers including Itai Yani at NYU, started digging into a gene called TBXT, a gene long known to play a critical role in tail development across vertebrates. When they compared TBXT across tailed primates and tailless apes, they found something unexpected sitting inside it. A small piece of extra genetic material called an ALU element had inserted itself into the gene at some point in ape evolutionary history. ALU elements are sometimes nicknamed jumping genes because they're small mobile fragments of DNA capable of copying themselves and inserting into new locations throughout the genome, usually without causing any noticeable effect at all. The human genome is packed with these things. Over 1 million copies scattered throughout our DNA, the overwhelming majority just sitting there doing essentially nothing. Except this time, it did something. A big something. That ALU insertion landed in a spot that interfered with how the gene gets processed, triggering something called alternative splicing. The cell's machinery started reading and assembling the gene's instructions slightly differently, producing a shortened, altered version of the TBXT protein. And that altered version appears to disrupt tail formation during embryonic development. The researchers didn't just want a compelling story sitting in a genome comparison. They wanted proof that could hold up under scrutiny, not just sound convincing in a meeting. So they engineered this specific genetic change directly into mice. And the mice grew little to no tails. Let that sit for a second. A single specific genetic tweak, isolated by researchers chasing a hunch that started with a kitchen accident, was enough to dramatically shorten or completely eliminate tails in laboratory mice. That is about as close to solving a 25-million-year-old evolutionary mystery as modern genetics gets. But here's the twist inside the twist. And this is the part that makes the whole story darker and far more interesting than a simple "we found the tail gene" headline. The mice with this engineered mutation didn't lose their tails cleanly. Some of them also developed neural tube defects, the same broad category of birth defect responsible for conditions like spina bifida in humans, where the spinal column doesn't close properly during development. In other words, the mutation that likely helped our ancestors lose their tails may have come bundled with a real biological cost. Not a clean upgrade, a trade-off. This isn't just an abstract footnote about ancient ape evolution either. Neural tube defects remain a real, ongoing concern in human pregnancies today, affecting a meaningful number of births worldwide every year, which is exactly why doctors emphasize folate intake so heavily during pregnancy. It's genuinely strange to consider that a small genetic scar left over from a 25-million-year-old mutation might still, in some roundabout evolutionary sense, be tangled up with a modern medical concern that expecting parents are warned about at every prenatal appointment. Think about what that implies. Around 25 million years ago, a genetic change swept through the ancestral ape population. A change that removed the tail but simultaneously nudged up the risk of a serious developmental defect. And it stuck around anyway. It spread through the entire lineage, becoming permanent in every ape species that followed, humans included. Which means whatever advantage came with losing the tail must have been significant enough to outweigh that increased risk generation after generation for millions of years. So what was that advantage? This is where the story shifts from pure genetics into behavior and movement. And honestly, it makes a lot of sense once you picture it. Around the time apes lost their tails, their movement style was shifting dramatically. Monkeys tend to move quadrupedally along the tops of branches, using a long tail as a counterbalance while running and leaping. Apes increasingly relied on a completely different strategy called suspensory locomotion, essentially swinging below branches using their arms. A style you can still watch gibbons perform today with genuinely alarming speed and precision. A balancing tail becomes a lot less useful when you're hanging beneath a branch instead of running along the top of one. In fact, a long trailing tail might have actively gotten in the way, a dangling liability rather than a helpful counterweight. Losing it may have streamlined this new style of movement, freeing up energy for a body plan that was rapidly specializing toward upper body strength and shoulder mobility instead of tail-based balance. Watch footage of a gibbon flying arm over arm through a rainforest canopy sometime, and it becomes obvious pretty quickly that a long, dangling tail would be less of a helpful accessory and more of an unfortunate way to get tangled in a branch mid-swing. This shift in locomotion didn't just shape how apes moved through trees. Many researchers believe it laid essential groundwork for what came later in the hominin lineage. Increasingly upright posture and eventually full bipedalism, a body already restructured around vertical climbing and arm-supported movement rather than four-legged running with a counterbalancing tail may have been considerably better positioned to eventually actually stand up and walk on two legs. So, in a strange, roundabout way, that ancient genetic accident, one tiny piece of jumping DNA landing in exactly the wrong, or perhaps exactly the right spot inside a single gene, may have quietly set the stage for the entire trajectory of human evolution that followed. No tail meant a different way of moving. A different way of moving eventually meant, and walking upright meant, hands were free for absolutely everything that came next. Tool use, complex manipulation, eventually building entire civilizations, all resting on a foundation that started with losing something as seemingly minor as a tail. There's one more strange detail worth mentioning before we wrap up. Every so often, medical literature documents extremely rare human cases where a baby is born with what doctors call a vestigial human tail, a small, soft tissue protrusion at the base of the spine without any actual vertebrae inside it. These cases are exceptionally uncommon and typically resolve with straightforward surgical removal, but they're a genuinely striking reminder that the ancient biological instructions for building a tail haven't fully vanished from our genome. They're still tucked away in there, mostly silent, occasionally, very rarely, slipping past the usual developmental override. It's a bit like discovering your house still technically has the wiring for an appliance nobody in the family has used for several generations, quietly dormant behind the walls, waiting for a circumstance that almost never comes. So the next time you catch yourself absent-mindedly rubbing your tailbone after sitting too long on a hard chair, remember what you're actually touching. Not some random leftover bone with no story behind it, but the final remnant of a body part your ancestors relied on for millions of years, deliberately switched off by one small accidental genetic insertion that happened to arrive with a hidden cost attached and turned out to be worth it anyway. 25 million years of ape evolution, an entire family tree stretching from gibbons to gorillas to us, quietly traces back to one jumping gene that happened to land inside one particular spot in one particular ancestor's DNA. No grand plan, no dramatic event, just a small molecular accident that stuck around long enough to become permanent, carried forward silently through millions of generations until it eventually became something you could actually go looking for, cut your finger, and stumble into discovering almost by accident all over again.